I want to talk about the length of a curve. And in particular, I want to talk about the length of a curve from a starting point to an end point, where that curve is a path determined by a vector valued function with a given starting point, A, and a given ending point, B, for my parameter t. Now you notice that I called the curve C, and then I've rewritten it in sort of a parameterized form, similar to how we wrote our equations for lines back when we were writing equations for lines. X is equal to whatever the x component is, y is equal to whatever the y component is in my vector valued function, and t is not an element of arc. T ranges from A to B. I start and I stop. So there's some path I'm following, or some path part of me is following. Some path a rocket ship is following, a fish, a bird, a bug, a car. It's a path. So the path starts and it goes up and it works its way down and then it comes back up again and stops. So it starts, goes up, down, smoothly back up again. Could be a dance move. I would like to know how long that curve is, how far we've traveled from start to end. Now, get to pull out some Calc 2 stuff. And I get to say fundamental theorem of calculus at some point. Yeah, this isn't so straightforward to do at first, but if we impose a little bit of calculus on this, we can make this straightforward. It'll take a little while, but let's say that we've got a point 1 right here, x1, y1, and another point that's not really that far away, x2, y2. Now, if I connect those 2 points with a line, then on this video, that line is almost indistinguishable from my curve. And of course, as I make those 2 points closer and closer together, it is even harder to distinguish between the line that connects 2 points and the curve that wobbles between them. Distance formula for finding the distance between 2 points, I'm going to denote that by delta L, because these are just 2 points on the curve, and I want to find the change in the length of the curve between those 2 points. Now, I'm not going to get it perfectly by using a distance formula because my curve curves. My line is straight, but my curve curves. Maybe just a little bit, but it curves. So I can approximate that with the square root of the difference between the x values squared plus the difference between the y values squared. So I can approximate the change in the length of my curve from one point to another by looking at your standard distance formula. x2 minus x1, change in x. y2 minus y1, change in y. Now what I'm going to do next is going to seem like I am pulling something out of a hat. I'm not pulling something out of a hat. I'm doing something intentionally so I can get back to, oh my gosh, where did that curve come from? It came from a vector valued function. So how can I get back to my vector valued function? I need t back. T just went away and I need it back. Well, this is some particular t value, and this corresponds to some particular t value, but I really don't care about that right now. I am going to use the expression delta t to represent the change in time from being here to getting there. So I follow the curve. What's the change in time from one point to the next? Well, hold up. I can't just throw a delta t on the outside of that square root. I got to make sure that I multiply by 1 so that I am not changing anything and I still get to use my squiggle or my equal sign. So if I were to divide by delta t, yeah, okay, then I'm multiplying by 1, right? And then what if I were to take that over delta t part and slide it inside of my square root? Then what it's going to become when I slide that into the square root is delta t squared. And I'll go ahead and use the distributive property and distribute that over the two terms inside my square root. Oh my gosh, you know what? I can rewrite this a little bit better. Delta L is approximated by the square root of delta x over delta t quantity squared plus, I never make my bars at the top big, delta y over delta t quantity squared and the extra delta t on the outside. Now that's just for the 2 points that I picked and the change in time for those two. If I were to come into this curve and mark off a whole bunch of points and do this same computation, which I could do, the same computation for each pair of consecutive points, and then add all of those up, then I would get an approximation of the total length of the curve. And since I'm saying arc length for curve length, we use L. It's approximated by the sum of all of those delta L's from here to here, here to here, etc., etc., etc. Add up all those little distances, and I get an approximation. And I know I didn't make my square root top there big enough. It's an occupational problem that I've never solved. So a good Calc 1 question to ask now, or a good Calc 2 question to ask now is, how do I make my approximation better? What can I do to make my approximation better? I've got all these points that I picked, and I want a better approximation for the length of my curve. Let's think back to originally what our variable was. Our variable was time. So let's make my time steps smaller. So instead of going 1 second, 2 seconds, 3 seconds, 4 seconds, let's go 1 second, 1.1, 1.2, 1.3. Tinier little pieces of my curve will pop out. And so as I add those tinier pieces together, I get a better approximation of the true arc length. So in other words, I'm going to let the time step in between 2 points get small. I'm not going to let it be equal to 0. I'm going to let it get small. Limits are not about what happens at a specific value. Limits are about what happens when you get close to a specific value. So if I take the limit of a sum of something, and again, that's in the way. fundamental theorem of calculus, or at least one version of it, leads me to my next step. I have a sum over a bunch of tiny little steps in time. What is my distance between 2 points as I walk along that curve with tiny little time stamps? My arc length, the fundamental theorem of calculus says, one of the versions of the fundamental theorem of calculus says, this will be the integral from the start to the finish of the square root of, now you know your tradition, let's change those Greek letters to Latin letters when we throw a limit in front of it. Oh my gosh. Okay, so if I change the deltas to d, I've got dx dt. Dx dt, that's Leibniz notation for the derivative of x with respect to t. The derivative of x with respect to t. The derivative of x with respect to t. What's another way to write it? I can go back to my vector valued function and say, oh, the derivative of x with respect to t is the derivative of my x component of my vector valued function. Delta y over delta t, limit as delta t goes to 0. That becomes dy dt. Dy dt is Leibniz notation for the derivative of y with respect to t. The derivative of y with respect to t. Where did y come from? G of t. What is the derivative of g? I don't know, because I don't know what g is, but I'll just throw a prime on it. And again, extend my square root symbol. Slide that dt over so you don't think it's stuck inside of the square root. And when you are given a vector valued function and you have a starting point for t and an ending point for t, you know when you start, you know when you stop, and you want to find out how far you've gone by following the endpoints, the terminal points of all of those vectors you would get for all of the t values that range from a to b. When you plug them all into that vector valued function, arc length. I don't even have to know what the curve looks like. So that concept of parameterizing the curve, yeah, okay. So sometimes when I know what the curve looks like, I can answer the question fast. So if it turned out I had a half a circle, then I could figure out the length, okay? If I discovered I had a line segment, I could figure out the length. The integrals aren't always going to be easy because you have square roots and squared things. So sometimes the work that you have to do to get to your final answer for what is the arc length is a lot. This is one of the few places where trig substitution may come into play. Good news for you. I'm just going to ask you to set them up and not evaluate them. I know that sounds like I'm not asking you to do enough, but you know what? There are tools out there for you to evaluate integrals once you have them set up. The setting up is the important part. We have technological tools out there for us. And you've already shown somebody that you can do these integrals, or you wouldn't be in this class with me. So I don't need to see what you showed somebody else. What I need to see is that you can interpret a question such as, here is a vector valued function. Here is the range of t values. Find the length of the curve. Surprise! I have 3D up here now. It's because I don't care about drawing anymore. And you may wonder how I get away with this. You know what? Every step I did in that derivation would just have a third something squared tossed onto the end, a change in z squared. It would all work out the same. Oh, look. There it is. When you only have 2D, you cut off the third term. I don't need the plus there. All right, I want to find the length of the curve that is governed by this vector valued function. R of t is equal to 5t as the I component, 4t squared as the j component, and 3t squared as the k component. Now you notice I chose to use the bracket notation just because I haven't used it much of late. And I want to show you one other thing. It might be presented to you as saying, oh, x is 5t, y is 4t squared, and z is 3t squared, and t ranges from 0 to 2. So you might see the problem presented to you this way, and you might be asked, find the length of the curve. Well, however it's presented to you, I have x, y, and z, and I have them as functions of t, and so I can find their derivatives, pop them into that formula, and hope for the best. Let's see what happens. The length of my curve from t equals 0 to t equals 2 is equal to square root of something dt. What's the something? The derivative of x with respect to t squared. What's the derivative of 5t? 5. The derivative of y with respect to t squared. The derivative of z with respect to t squared. And then clean it up. Because you always want to clean up your integrals before you decide how in the heck am I going to evaluate said integral. All right, that's 25 plus, all right, 8 squared is 64. 6 squared is 36. 64t squared plus 36t squared is 100t squared. Ooh, you know, I say that I don't care about simplifying radicals, but in this case, I kind of wanna. 25 is a factor of both terms on the inside. So I'm going to factor 25 out of that square root and rewrite this as 5 times the square root of 1 plus 5t squared dt. I asked you, what's the length of the curve? Have you ever looked in the back of your book? I know there's tools out there on the internet, and I know some of you have really great calculators, way better than the calculator I've got. Way back in the back, there is a table 4. I know it's blurry. Table 4 called the table of integrals. In my book, it's on page A for appendix 21. It is appendix 4, table of integrals. And I look and I see if I can find something similar to my integral. Oh my gosh, I found it in the middle of the page. Lucky me. So if we try to apply Formula 21 from Appendix 4 on page A21 in our calculus textbook, to our arc length integral. We'll have to make some adjustments because u and 4t squared, u squared and 4t squared don't exactly match up. dt and du, some adjustments have to be made. It's just a matter of matching. Now, once I match, I'm going to get to drop the plus c down there on the end of the formula because I have a definite integral. So let's focus on the matching part. Where this formula is coming from is trig substitution. And if you don't remember, when you're doing trig substitution, you always do trig substitution on a right triangle, which means your angles that you're dealing with, the non-right angles, are acute angles. So in trig substitution, you never have to worry about negative lengths. You only take positive lengths. And so when I'm making my adjustments here, because I know due to the fact that this is the square root of the sum of squares, or if it was the square root of the difference of squares, trig substitution is what's going to leave me here. And I don't have to worry about negative values. So when I look at 1 and I look at a squared, what do I square to get 1? Technically minus 1 or 1. But I'm going to match a to 1, not negative 1. Because, again, this is coming from trig substitution, so it would be the length of a side of a triangle, and I wouldn't refer to that as a negative. What do I square to get 4t squared? I square 2t. So now it's almost just a u substitution problem if you're willing to go ahead and use some of these formulas in the table of integrals in the back. Now, if u is 2t, that means that du gets replaced by 2 dt in this formula. Or dt in this formula gets replaced by 1/2 du. And this is where I'm going to go back and make my adjustments. So I'm going to convert this formula into this one and replace the t's with u's. Now nothing's going to happen to this 5, and my limits of integration I'm going to leave alone for now. I want to match this 1 with this a squared and write it as 1 squared. U is going to take the place of 2t squared. So 4t squared gets replaced with u squared. Du and dt aren't identical. So what do I replace dt by? 1/2 du. Now, ignoring my question marks here for the limits for u and ignoring this 5/2 out front, everything else looks like this formula number 21 in the back of my book. So I'm ready to go ahead and start plugging stuff in, replacing these u's with the t's. So this step was just to make sure that I was matching things correctly and that I really did have this form of an integral. And once I know I have this form of the integral, then I can use these substitutions to go in and fiddle with all of this. That 5/2 is not going anywhere. The integral of square root of a squared plus u squared du is equal to u over 2 times the square root of a squared plus u squared plus a squared over 2 times the natural log of the absolute value of u plus square root of a squared plus u squared And now, because I do have a definite integral and I brought t back, I can evaluate that from t equals 0 to t equals 2. Now, if you want to slide this 5/2 through, that's fine. If you want to keep the 5/2 out, that's also fine. There is just a small amount of cleaning that I would do before I plugged in any numbers, and I'd simplify this to t square root of 1 plus 4t squared. I'd simplify that to 1/2, and then natural log of 2t plus square root of 1 plus 4t squared. And then remember, we evaluate from t equals 0 to t equals 2. And of course, I'm down at the bottom of my board again, so I have to erase and move things up. The 5/2 is in front already. This is a simplified u over 2. This is a simplified square root of a squared plus u squared. This is a simplified a squared over 2. I'm looking down at the formula in my book. This is a simplified u plus square root of a squared plus u squared. And now, t equals 0 to t equals 2, plug in the top, subtract what I get when I plug in the bottom. My 5/2 is still hanging out in front. Now there's a couple of these that are going to be nice. When I subtracted what I get when I plug in the bottom, I have a 0 for t, so that term is gone because it's just 0 and I don't have to worry about it. 2 times 0 is 0. 0 squared is 0. 4 times 0 is 0. 1 plus 0 is 1. And the square root of 1 is 1. So really inside this natural log, all I have is a natural log of 1, which is, what's the natural log of 1? It's 0. Natural log of 1 is 0. So I don't have much to clean up now. I got my 5/2. I have my 2 square roots of 17 right here. And then a 1/2 natural log of 4 plus the square root of 17 right there. Close it off, and I'm done. The only tiny adjustment I might make is natural log is only defined for positive numbers, which is the reason why when we integrate and a natural log pops out, we throw those absolute values around it. Well, 4 plus square root of 17 is a positive number. So, voila, there is the length of my curve from time 0 to time 2. Use those formulas in the back of the book in Appendix 4 to help you. More often than not, it's going to be that first one, number 21. If I ask you to evaluate an integral to represent arc length, if you want to do trig substitution by hand, let me warn you, you're going to end up with a secant cubed integral, which means you're also going to have to use integration by parts, which means you're going to have to back substitute a few times before you get back to your t's. I'm not going to stop you if you want to do it that way.